Okay, picking up where we left off with the flipped lesson, if you watched it last night. Last night was just an overview, like here's ionic. What are ionic ones doing?
Bonding.
Well, they're all bonding. They're transferring the electrons.
They're
They're giving and taking. And then covalent are sharing. Okay, so don't be ionic, be covalent, carrying and sharing. Okay, all right, so here are some vocabs we need for covalent compounds. First thing is a molecule. And a molecule is a neutral group that are held together by covalent bonds, being they're sharing their electrons. A molecular compound is how we refer to them. A covalent bond will form a molecular compound. That's going to be important when we start doing naming on the next unit, which is nomenclature, because we name our molecular compounds, which are sharing their electrons, differently than we name our ionic. Okay? Chemical formula is used for both ionic and covalent compounds, and it's basically telling us how we recognize how many atoms are in our formula. So, for instance, Mr. Wells, what is the formula of water? I'm giving you a really hard one. H2O. So that means we have two H's, one O, right? How about Bailey? What is the formula for carbon dioxide? CO2. CO2. And then table salt. Who wants to give me table salt? Yes.
NaCl.
NaCl. All examples of chemical formulas. Okay. NaCl would be ionic because it's a metal and a nonmetal. The other two would be covalent because they're two nonmetals. Okay. Continuing on with covalent, we need to recognize our diatomic molecules. This is about the third time and about the third unit that I've shown you diatomic, so they must be really important if I keep showing them to you. Repetition helps you remember it. Remember, those are the ones we call the Brinkelhoffs, and that is when they are by themselves only, then they're diatomic. Bromine, iodine, nitrogen, not nickel, I don't know where that came from. It's the end of the day, I'm tired. Chlorine, hydrogen, oxygen, and fluorine. And remember, it's only when they're by themselves. So if I tell you I have oxygen gas, you would write O2 because that's its natural state. If I said hydrogen gas, you would write H2. Here's where most kids make their mistake. They think they're always Brinkelhoff all the time, whether they're in a compound or not a compound. But they are only diatomic when they're by themselves, all alone in the world. They join up 2 by 2. Okay? So an example of that would be, what is the formula of glucose? I know in biology they drove that into your little brains. C6H12O6. Hydrogen and oxygen, both diatomic molecules, but in a compound, they're 12 and 6, respectively, in glucose. So they're whatever they need to be in a compound to share appropriately. They're only diatomic when they're by all in lonesome. Okay? How is a bond formed? And that is, it is the nuclei of one atom being attracted to the valence electrons of the other nearby atom. Okay? Because it still has to be a nucleus that's pulling in on those electrons, because opposites still attract. So if I can get my nuclei of one atom close enough to the valence electrons on a nearby atom, I can form a bond. They do so when the optimum distance is reached in which the potential energy is lowered or minimized. Nature will do this in order to lower the potential energy. Nature likes things in its lowest form of potential energy as possible. Okay? All right. The characteristics of a covalent bond are the bond length and bond energy. Bond length is that distance at which that potential energy is minimized. So there's like a perfect little spot where the energy is minimized, they're not repelling, they're not pushing each other away, so that's like the sweet spot. Bond energy is the energy required to break a chemical bond. It requires energy to break a bond. Energy is released when a bond forms. Okay? And we report that in kilojoules per mole. If it has a very high bond energy, that means that it's a hard bond to break. The octet rule is saying that chemical compounds tend to form so that either by gaining, losing, or sharing their electrons, that the valence electrons of that particular atom has an octet. And so if it's a metal, it'll lose electrons and usually get to that octet underneath in the energy level below the valence electrons. If it's a nonmetal, they'll gain and complete the outer energy level that they're already adding electrons into. There are some exceptions the most obvious exception should be hydrogen, right? It only has one valence electron. Is it going to share or gain 7? Probably not. Okay, so it will either share to get what's 2 electrons in the 1s, which we call a duet. Makes sense. An octet's 8, a duet is 2. Or it will give it away and just be a proton. So if it gives its electron away, it has no neutron. Basically, a hydrogen ion is a proton. Also, some of the other exceptions are helium. Please don't ever tell me that even though it's in group 18, please do not tell me that helium has 8 valence electrons. It only has 2, 1s2. That's it. Okay. Boron is another example because it's got 3 valence electrons. So it's usually going to share the 3 that it has and form a total of 6 bonds, but only 6 electrons. And then what happens to lithium? It's one of another exception. Lithium gives away its valence electrons. How many will it have in its outer shell? 2. Exactly. I don't know who said it, but good job. It'll have 2. Okay? And then some can actually have an expanded octet and have more than 8. Electron dot notation is a new kind of electron configuration that we're going to show, and it's basically the outermost S&P orbitals. So our valence electrons, we're going to draw dots around the symbols. Okay? And so y'all are going to do this with me. I put them in your notes. Sodium is a group 1 metal. How many valence electrons does it have? 1. So I'm going to draw 1 dot to represent 1 electron. So dot. Okay, it does not matter where you put that dot. Okay, you could put it on the left side, the right side, up side, or down side. Okay, it doesn't matter. It will matter slightly on the next one because on the next one, magnesium has how many valence electrons? 2. So I want to put them as far apart from each other as I can. Plus, if you recall, Hund's rule states everybody's got to get an up before they get a down. So every side has to get 1 electron before they can get a second. So I'm going to draw them as far apart as possible to minimize those electron-electron repulsions. How about boron? How many valence electron? It's group 13? 3. So 1, 2, 3. We drew them as far apart as possible. And then how about carbon? 4. So 1, 2, 3, 4. And nitrogen? 5. So for the first time, we're going to pair up. There's going to be 2 dots on one side. Again, it does not matter what side we do that on. So 1, 2, 3, 4, and we're going to pair them up there. I like them to look like they're together. There. Now they look like they're together. Okay? Oxygen has how many? So now we're going to have 2 sides paired up, right? 1, 2, 3, 4, 5, and 6. Now those are good looking dots. How about fluorine? 1, 2, 3, 4, 5, 6, 7. And then neon? 18. Not 18. It's group 18, 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now, we have already said what metals do with their electrons. What do metals do with their electrons? They give them away. So these right here, they're going to send their electrons packing. Say, see ya, wouldn't want to be ya. Okay, so they're going to look different. But all of these other things are going to either take electrons or share electrons. Okay? And where they can share electrons or where they can take electrons is where we have a dot with an empty spot. Or in other words, we don't have 2 dots. So on boron, it can form how many bonds? 3. How many bonds can carbon form? 4, because it's got 4 empty openings or empty slots. How about nitrogen? 3. Oxygen?
2.
Fluorine? Neon? None. Okay? So when we draw these electron dots, it kind of shows us how these things are going to bond together. Okay? Which brings us into Lewis structures. We're going to use electron dot to draw Lewis structures. We're going to do a very light version of Lewis structures today just so you can see what they are. And then Friday, we will be doing Lewis structures and molecular geometry for much bigger structures. Okay? And I've got like a little list that tells you how to draw them. So if you don't understand what I'm doing today, just hang on till Friday. Because tomorrow is Mole Day. Yeah. Okay? All right, so Lewis structures look like this. We're going to join these things together. And we represent our bonds by two ways. We already know we're representing the electrons by the dots, right? So we can represent the bonds either by a dash, like a line, or we can just draw the dots to represent the two that are being shared. Okay? So we're going to draw what the Lewis structure of hydrogen and fluorine individually look like here at the top, so we can see. Well, those are some sad looking. Let's draw that again. Apparently I'm not good at straight lines or putting dots in a straight next to each other. So that's what their individual Lewis structure or electron dots look like. So in this first one, I want to join up hydrogen and helium. So what am I going to do? They each have one slot that they can share. So what they're going to do is they're going to make a little bond, and they're going to share those right there. And that's going to represent our bond. So we can draw it like this, saying, and then give these over here to fluorine, or we can draw it like this, H-F, and then go back and give fluorine its own electrons. Okay? So hydrogen, we said, was an exception. It will not get 8. It will only get 2. And so if I look at this structure, hydrogen now currently has 2 electrons available to it to share, right? So it's got its duet completed. And then how many electrons does fluorine have total? 8. It's got its 6 that belong just to it, and then it's got the 2, one that it's from hydrogen and one from it, and they're sharing. And the ones that they're sharing belong to both atoms, and they will spend time in both orbits around the nucleus. Okay? If I was going to do hydrogen and I put hydrogen together, what would it look like? Whoops, that's a thick line. Sorry. I have that line for when I draw the dots, they draw thicker, or I can draw it like this. The 2 dots or the 1 dash or the 1 line mean the same thing. You just have to remember when you're drawing the line like this right here that means there's 2 electrons. Okay. And then how would I join fluorine up? So we would say they're forming a bond there, which is representing how many electrons? 2. I like to do my thicker pen because then I can just literally dot it. Okay? So that's what they would look like. So the fluorine is sharing 2 electrons, and then it has 6 electrons that just belong to 1. They don't share those. Okay? And those ones that just belong to the one particular atom, we call those lone pairs. So the lone pairs are those ones that just belong to fluorine. They didn't share those. And then the bonded pair is, of course, the pair that they're sharing. And then structural formula is we would literally just draw the lines. And we wouldn't draw the lone pairs of electrons. Okay? Are we good so far? All right, continuing forth. So single bonds are covalent bonds that are produced by sharing 1 pair of electrons. Okay? Well, these things have the abilities, not everything, but some things have the ability to form what's called multiple bonds, and they can double and they can even triple bond, some of them. Okay? So, example, carbon and nitrogen, they can single bond, they can double bond, and they can triple bond. And then sulfur got left out of your notes, oxygen and sulfur, they can double and single. Now, there's one exception for oxygen, and that's when it forms carbon monoxide, and it can actually triple bond. And it's one of the few exceptions of oxygen triple bonding. Also, one of the few times you'll ever see lone pairs on carbon. Typically, carbon will not have lone pairs. But carbon monoxide is an extenuating or an exception to the rule. So what does a double bond look like? It looks like 2 lines. Carbon, we said, we're going to join these up. Carbon has how many valence electrons? 4. 1, 2, 3, 4. How many does oxygen have? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I need to join up. Carbon needs 4 bonds. Each oxygen can only hold 2 bonds. So how could I get 2 things that have 2 bonds to join up with one thing that has 4 bonds? Here's a hint. double bond it. So here's what happens. This can share, so it says, hey, I'll share with you here, I'll share with you here, I'll share with you here, I'll share with you here. So then we would say double bonds, double bonds. So now currently, how many electrons does carbon have available to it by sharing? 8. 8. Each line represents how many electrons? 2. So there's 4 bonds times 2 electrons gives me 8 total electrons. Oxygen is now missing some though, right? And if you go back and you look at, oh, wait a second, look, oxygen had some lone pairs here and here, and it had some here and here. So I still need to give oxygen its lone pairs that belong exclusively to oxygen. And I'm going to draw those as far apart as possible, minimizing those electron repulsions. Okay? So that is what carbon dioxide looks like. CO2, what you're breathing out every day. And what the plants are taking in and forming glucose. And then let's represent a triple bond. So nitrogen, nitrogen. How many valence electrons does nitrogen have? 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So it needs to fill up all of its slots. So guess what it does? I'll bond with you here, here, and here. So that my nitrogen looks like this. At this point, the way I've drawn it, how many electrons are they sharing? 6. So we got to give the lone pairs to each nitrogen. And those lone pairs belong exclusively to that nitrogen. The 3 bonds that they're sharing, those 6 electrons belong to both. They're sharing them. In this case, they're sharing them 100% equal because they have the same electronegativity, so the same attraction for that electron. Okay, so to recap, single, double, and triple covalent bonds are sharing 2, 4, 6 electrons. You do not have to draw the examples. I'm just showing you a visual of what that looks like. Remember, each line is representing 2 electrons. Two, 4, 6. You got that written down? All right. Of those 3 bonds, single, double, or triple, which would you expect to be the strongest? Which would you expect to have the highest bond energy? The triple. That makes sense. You are right. It's not one of those things that's opposite. It is very much the truth. So if you have a single bond, you have a lower bond energy and a longer bond length because they're further away from each other. So let's go back to Coulomb's law, and if your distance is further, you're going to have a lower attraction, hence a lower energy to break the bond. Whereas if you look at a triple bond, it's much, much shorter, which means, according to Coulomb's law, have a smaller number on the bottom, dividing by a smaller number would give you a larger attraction, require more energy to break. Okay? All right. So that's going to take us to resonance structures. And basically what resonance structures are we're drawing these things in 2D, right? I'm drawing them on paper. Some structures can't be represented by just one drawing, okay? And it's going to be if they have a double or a triple bond, because we don't necessarily know where that goes. And so the main thing that you need to know is that we represent that by a double arrow, okay, if it's a resonance structure. So ozone, which is O3, is going to be my example. I have got 0, 0, 0. I'm going to name myself. Double arrow, 0, 0. So those aren't zeros. They're O's. So ozone, we know from experiment, has a single and a double. Okay, how do I know which one is the single, which one is the double? And the answer is I don't. So I represent both ways. So I'll say I'll draw a single here and a double, and then I'll do the double here and a single. And now I'm going to go back and give everybody, make sure they have 8. So this one needs 6 more, 2 more, 4 more. 4 more, 2 more, 6 more. And so those are the resonance structures of ozone. And this double arrow right here is how we represent that. Both are equally probable. And so we have to draw them. Both are equally probable, so we represent that with the double arrow. And that's truly all you really... Well, first of all, you need to know that some things have resonance structures, and that we represent that by the double arrow. Okay? All right, that brings us to ionic bonding. And, of course, ionic bonds are doing what with their electrons? Giving and taking, transferring. So they're outright. They're not sharing them. I'm outright giving you my electron, or I'm outright taking your electron. Okay? Ionic compounds are composed of positive and negative ions that are combined so that the numbers are equal. Okay? It's an electrostatic attraction, right? And you'll be surprised, or I'm always shocked at the amount of people who miss that on a test when it talks about what bonds have positive and negative ions. And I'm like, it has the word ions in the name. How are y'all missing that? Okay, so make sure if you see ions, it's an ionic bond, right? Most crystalline solids, most of them are solids and they're crystals. They're always going to be between a metal and non-metal. Okay? So if you see a metal and a non-metal, just say it's ionic. The formula units are the simplest collection of the atoms from which an ionic compound can be established. So if I have one formula unit, it would be, like in this case, it would be 1 sodium, 1 chlorine. That's a formula unit. Okay? In the beginning of the year when we were doing dimensional analysis, remember it said how many molecules of something we have, how many formula units of something you have, and it was kind of throwing y'all. All that means is when I say the word molecule, I mean it's covalently bonded. If I say the word formula units, it's ionic. Okay? The way that we show the electron dot or the Lewis structure for ionic compounds is we're actually showing the transfer of the electron. So we're not going to draw a bond, we're not going to draw a line, we're literally saying, hey, this electron is going right there. And then when I draw the electron dot for sodium, I draw it with 0 electrons because it has no more valence electrons. It gave them all away. So it's got a +1 charge because it gave away 1 electron. And then chlorine, I show is now having a full octet because it gained 1, and I show it with a negative sign. Characteristics of ionic bonding. Nature favors an array. Oh, this is like the second or third time I'm saying this. Must be important. Potential energy is minimized. Okay? So by giving or taking an electron, that cation or anion forms an octet, which stabilizes it. Okay? The crystal lattice is the arrangement. It's kind of like the bond length when we were talking about covalent. Crystal lattice is that arrangement in which the potential energy is minimized. Okay? And it is going to be alternating. Positive, negative, positive, negative, positive, negative. Okay? Because if I put like ends of a magnet together, they repel. But if I put opposite in, they will attach, which is very similar to what these ions are doing, kind of like a magnet. And then your lattice energy is the energy released when 1 mole of ionic compounds is formed. So just like before, when bonds are made, we're releasing energy. There are 2 types of ions. One is monoatomic, that means 1, like sodium ion, Na+, magnesium ion, Mg2 +2. But there's also something called covalently bonded polyatomic ions. So I want you to add that here. These are covalently bonded with a charge. So although they are covalently bonding, meaning they're sharing electrons, when they do so, they have a charge, so they will join up with something with a charge and be ionically bonded. So if I showed you something like this, CaSO4, and I asked you what type of bonds were present, you would say both. Because the SO4 is covalently bonded, but then it ionically bonds with that metal of calcium. Okay, so if it's got one of those polyatomic ions, it's going to be both. Now, there is a huge, giant list of polyatomic ions that I'm going to give you on Thursday, and then next week we're going to have a quiz over them. But I'm not giving it to you tomorrow because tomorrow is all day. Yeah. Which is why we're getting so much notes at one time today. Normally I don't like to do this many at one time, but it was either squish them all in today or not have them all day tomorrow and have to do work. Okay? Last section, I promise, metallic bonding. Metallic bonding are delocalized electrons. So they occur between two metals. They result in the attraction between the metal ions and the surrounding sea of electrons. My favorite way to explain what metallic bonding is this is the socialist of bonding, because the electrons belong to everybody equally. They share them all. No one gets to work harder for the electrons. They all get them, no matter how much the other ion in the form of the nucleus worked for them. Okay? They belong to everybody. Which is why they are such good electrical conductors, because I can start a current on one side and that electron can carry it all the way through because it belongs to everybody. Okay? So that's what's going on, is they're moving around, not belonging to any one ion. And that's true whether it's two metals of the same, like if I have a gold bar, or if I have a metal alloy, which is two different metals mixed together. Your metallic properties, conductivity, this is why, because they have these delocalized electrons. They have multiple orbitals. Many of them are in the D block, and they have other orbitals available to them. They are luster or shiny, which is because of the photoelectric effect. And then those classic metallic properties that I don't think at this point in your life I need to define: malleable, ductile, all that stuff. You already know that, right? Anybody not know what malleable is at this point in your life? Good. If you can't remember, come ask me later. Metal alloys are the mixtures of elements held together by metallic bonding. Those are things that the reason they make metal alloys is together they're a better material. For instance, what does iron, pure iron, do if you leave it outside? It oxidizes and forms rust. Not good if you're building a building. You don't want your walls or your beams to rust. So they make carbon steel or that sort of thing, which is mostly iron, but they mix in some carbon. Or anybody ever heard of galvanized steel or galvanized pipe? It's got a zinc coating because it resists that corrosion. Most jewelry that's silver is not pure silver. It's sterling silver, so it's got some copper in there, because silver tends to tarnish or turn black. And so they mix these together to improve their qualities. And then bond strength varies with your nuclear charge. The heat of vaporization is the amount of heat to vaporize 1 mole of the metal. Usually it's a measure of strength. So if it's got a very high heat of vaporization, it's going to be a very strong metal. And then the last thing for today is this chart. And so I gave you that chart to pick up. You can fill this out. You can take a picture of it. And quite frankly, you don't have to do this, but this is a handy study tool because it's putting all of the 3 types in one handy chart. So instead of flip the notes, you can just study that for the test. Okay?